Welcome back. My name is Nischal and I am a graduate student from the University of Pennsylvania. In the previous lecture, you saw how to build a map of the surroundings using Hector SLAM and also on how to use the Hector SLAM to obtain the crude odometry of the car. Now that we have built the map, the next task is to know where we are on the map accurately. It's crucial to know where we are to decide where we need to go next. It helps us to plan the trajectory that we need to take based on the upcoming corners and also make precise control decisions on the speed and race lines. That is, we can decide at what speed we need to approach a turn and based on how steep the turn is and also how far away we are from the race line. Another piece of crucial information that we need to know is our orientation or heading in the map. It helps us to decide on the correction that needs to be applied to the steering so that we can avoid collisions with the walls and obstacles. In general, knowing where we are on the map helps us to decide what to do next. Hence, we need our car at all times to know where we are located precisely along with its position and orientation on the map. Localization involves estimating the position and orientation of the vehicle, collectively called as pose, as it moves and senses through the environment. One way of knowing this position of the car is by tracking it from its initial position. By measuring the amount of rotations on the left and right wheels using the wheel odometry that we saw in the previous lectures, we can calculate the distance travelled from an initial position and predict with some certainty about the car's pose on the map. Here, the green dot is the initial position. As it begins to move, the green path is the trajectory followed by the car as tracked by the wheel odometry. Similarly, even the odometry information from the Hector can be used for tracking. But however, both these sources are not accurate enough. These are because of various reasons. First of all, the method of measurement itself is not accurate. So longer you run the car, the more inaccuracies in the pose estimate. Another problem with wheel-based odometry is that it does not account for the wheel slippage. Such problems are very common on high-speed platforms like our car. Due to the high torque of the motors, the wheel spins at the same location even before the car actually starts to move. The odometry believes that the car has moved a certain distance even though the wheel is spinning at the same location. This yields an incorrect pose. Similarly, when odometry using Hector SLAM used suffers from similar drawbacks. The scan matching based odometry fails when the corridor is very similar, such as corridor with parallel walls over short distances. In this video, you can see that even though the car is actually moving and recording new scans, which are shown in red, the scan matching based odometry fails to record this because the surface is very similar. It finally realizes that the movement has happened only when there is a prominent difference in the scan at the end of the video. Hence, we need a solution that can compensate for the accumulated odometry error, which includes the error due to measurement, wheel slippage and failure of scan matching. Additionally, we must also be able to localize without providing an accurate initial position. In other words, we must be able to handle inaccuracies in defining our initial pose. One solution to this issue is to use Monte Carlo localization, which uses particle filters. Other options include the use of Kalman filters, which uses Gaussians to keep track of the position, and Markov localization, which uses histograms. To understand about Markov localization, we first need to look at how particle filters work. Let us see an example of a robot that moves in one dimension. The environment is a corridor with a few doors. The robot can move up and down the corridor. The robot also carries a sensors that can sense only the doors and also has a source of odometry. This source of odometry tells us how much far we have travelled from the initial position. Initially, the robot has no information about where it is on the map. The graph of position versus probability of being where it is on the map is 0. We call this graph as our belief state. It defines the probability of the robot being at a particular position. At the first time step, the robot senses a door. So the probability of receiving this sensor measurement in the corridor is given by Pz given x, where Z is the measurement, which is the measurement from the sensor, in this case whether it is a door or not, and x is the position. We call this our measurement model. It denotes the sensor reading against the position. Hence, a belief state of where a robot is at the map also has a very similar distribution. At the next time step, the odometry from the robot says it has moved a certain distance forward. So now we can update a belief state by moving forward the same distance. To this, we add some amount of noise to accommodate for the errors in odometry. This is called a motion update of the belief state. It is nothing but a previous state that has been updated with the odometry information. Now we perform a measurement update by reading data from the sensors again. Again, let's consider the robot senses a door. Hence, a probability of receiving this measurement in the corridor is the same. By convolving the measurement update from our sensors with our previous belief state, we get a new belief state. In our new belief state, there is a probability of being near the door too. This process is repeated for every time step, and at each time step, the location where the probability is high is the place we actually are located. However, practically the belief states cannot be used as a continuous function. This makes it very computationally expensive. Instead, we sample to produce discrete positions or points. Each of these sample positions is called a particle. Hence, we can represent our entire belief state as a discrete set of particle positions in the corridor. Each of these particle positions are associated with the probability of robot located at that position. Also, instead of using uniform sampling where samples of particles are drawn from equal distances apart, we draw particles from the places where the probability of the belief state is very high. So here we have more probability of being near the middle door. So more particles are drawn from this position. The other positions where the probabilities of being very low have less number of particles. Each of these particles are associated with a weight which is equal to the probability of the belief state at that location. That is, the particles near the middle door have a very high weight, whereas the particles that are near other doors have a medium weight, and particles in other positions have very low weights. We will look at sampling, how these particles are drawn, and how these particles propagate over iterations in more detail in further slides. Now let's look at a particle filter in 2 dimensions and also the process of using them in our car. Here we see a part of the map that is previously generated using Hector mapping. The black pixels on the map denote the walls and the grey pixels denote free spaces. The red arrow indicates a pose obtained from odometry, which is not very accurate. Let's use particle filters to minimize the error and localize more accurately on the map. First, we need to generate a set of hypotheses for our position. These are the discrete particles drawn from a Gaussian distribution of mean being our odometry pose and with some covariance that defines the size of the region around which we draw the particles from. We end up with a set of poses which are obtained by adding some noise to our odometry pose. For each of these particles, we orient the laser scan shown in the orange with respect to the particle's pose and then compute a correlation score. Correlation score S is calculated using this formula where A is the map, B is our scan. A bar and B bar are the mean values of the pixels of both the maps respectively. The walls have a value of 1 and the free spaces have a value of 0. M and N are the x and y coordinates of the pixels. These equations basically count the number of blacks and orange pixels that overlap each other. We repeat this process for each particle and record the correlation score for each. The particle that aligns well with the map has a very high correlation score compared to others. In this case, particle 6 has a very high correlation score. and this particle with the maximum weight is chosen as the pose of the robot of the current state. Hence, the drift in the pose of the odometry seen in the image on the left is corrected by the particle filter in the image on the right. We repeat this process of correlation for each sensor update. First, we propagate each of these particles we generated based on the distance and direction defined by our odometry. Then, we perform a correlation for each particle as described previously and record the correlation scores. The weights of the particles are kept track by normalizing and multiplying over time steps. The scores at a time step t is first normalized by dividing with the largest score at time t and then multiplying with the previous weight for that particle at time t minus 1. In this way, we can keep track of how well each particle performs and draw more particles from that neighborhood when needed. As we are multiplying weights over time, the particles with small weight reduce to a very small value over time, and the particle filter effectively has very few particles to produce good results. This graph shows the number of particles along the x-axis with weights along the y-axis. We see that over iterations only a few particles become very prominent. To avoid this, we resample the particles whenever the number of effective particles became very few. To avoid this, we resample the particles when the effective particles become very few and we reset the weights. Consider these yellow circles as the initial set of particles that we drew from our distribution. As they propagate over time, their weights change and few particles become very prominent over the others. The size of the blue particles denote their weight. The larger the size, the larger the weight. When the size of these blue particles become very large, the particles have to be resampled. This resampling is done by drawing more particles close to the particles that have a higher weight than those that have a smaller weight. Thus, the new set of yellow particles drawn have a higher density near the positions where particles with higher weight existed. All the particles drawn have the same weight, hence the particle filter begins from scratch. This graph is a plot of x and y position of each particle. Each arrow represents a particle and its orientation by the arrowhead. The size of the arrow also denotes the weight of the particle. Larger the weight, bigger the arrow. Over iterations, only few particles become very prominent compared to others. When this happens, the particles are resampled. We can see that particles that have more weight are resampled into smaller particles very close to it, and a very few particles exist away from it. With this procedure, we can make sure that no particle dominates and each of the particle has a fair chance to be prominent. Hence, now a particle versus weight graph resamples whenever few particles become very prominent, and when they resample, their weights become equal. This form of localization is computationally expensive. This is because we iteratively have to calculate the correlation for each particle. So, more the number of particles, the more time it takes to compute the pose. In order to optimize this, we use a sampling method called KLD sampling. This technique controls the number of particles based on the difference in odometry and the particle based location. Initially, when the position is unknown, the particle cloud is large, as seen in the first figure due to the uncertainty in the position. But as the car moves, the particles converge and the particle cloud size reduces. Thus, the KLD sampling culls the redundant particles and improves the performance. Now that we saw how particle filters can be used for localization, let's see how it is implemented in ROS. This is implemented as an adaptive Monte Carlo localization package, commonly known as AMCL package. The word adaptive refers to the KLD sampling. This package can be used for localizing with laser scans against a pre-existing map in 2 dimensions only. In the last part of the previous lecture, you saw how Hector SLAM provides a transform that can be used as an odometry source to localize in a map. The AMCL package provides another transform to correct the drift in the Hector odometry to localize more accurately on the map. So, to summarize, we need a sensor data, that is a LiDAR scan, an odometry source, in this case Hector odometry, and a pre-built map as an input for this package. This package is going to produce us with the correct pose of a vehicle and also the particle cloud for debugging purposes. Now let's see the AMCL package in action. Here we are using a map from the last lecture. The green arrow is the pose from the odometry and the blue arrow is the pose that is corrected by our AMCL package. It actually denotes the pose of a best particle. The particles here are represented in red arrows. The difference between the position in the green and blue arrows depict the pose correction performed by the AMCL. After traveling a certain distance, the error in the odometry becomes visible. This is evident from the gap between the green and blue arrows. Some important parameters that AMCL package allows us to tune are the minimum and maximum particle cloud size that the KLD sampling must adhere to. Making it too high can reduce the update rate, and reducing it to a very few particles will affect the localization accuracy. Minimum distance and angle update parameters decide how frequently to publish the corrected odometry drift. Again, making it too small provides bad localization due to insufficient samples. The initial pose gives us the ability to programmatically define the starting position of a car in the map. This can also be provided through the RVIS GUI. Finally, the covariance of the Gaussian distribution can also be set. This defines the spread of particles around the mean position. We shall see more about these parameters in the tutorial videos. Now that you know where you are on the map, in the next lecture you will learn about how to navigate and plant trajectories.